Hi everyone, I'm Yutong Zhang, and today I'm going to give a talk on simple and efficient ways towards AI alignment. First of all, I'm just a high school student in studying in Shanghai, and I'm very glad I have the opportunity to give a talk on this platform and share my insights with many other people. So, without further ado, let's just dive in. So this is my talk plan for today. So first, I'm going to review the LLM train process, from which you are going to learn about the significance of AI alignment in LLM training. Then we're going to introduce the direct preference algorithm and its variant and how it's derived from the uh, original RLHF algorithm. Then we're going to talk about the algorithm's application, and then we're gonna have a tutorial on the application of direct preference optimization, which is in all-in-one method. So first, we're going to talk about the significance of the AI alignment, and this is a comic strip generated by ChatGPT, and I prompted to generate a comic strip to show the significance of AI alignment, and this is what I get. It goes like this. I've programmed our new AI robot to maximize the number of cookies baked. It's optimizing for the ultra objective I've set. Hey, maximizing the numbers of cookies baked. They never say anything about them being edible. So we can see from the picture that the robot cooked some very nasty cookies, which obviously can't be eaten by human, right? So from here, we can know that it is very important that we align AI systems to the goal of the human, and we want them to be beneficial for all human beings, right? So let's review of the process of training an LLM, and we're gonna know why it's important to have the alignment process in the LLM training. So from this diagram, we can see that the training phase mainly consists of three parts, which is pre-training, fine-tuning, and prompting, right? So in the first part of the pre-training, I concluded into four steps. So first, we collect huge amount of data from the web, which maybe consists of newspaper articles or classical novels or blogs other people said, or a post from Reddit, or even just the raw HTML language. Then we're gonna perform data cleaning. Because we only want the model to learn how to speak language fluently without showing them the dark side of the human being. We don't want to see some harmful content from the web. So we may set some rules to filter them into good data to train a model, or as we have maybe some HTML from the web, there are a lot of duplication there, so we may perform some deduplication and many other transformation to our raw data to get refined data to train our model. Then we're going to transform the data into the format for training. So as we know, when we train an LLM, basically we are doing mathematical operations. And obviously we can't do the mathematical operation to the raw text from the web. Then we have to transform the data into the format of training, right? Which is tokenization. So token is basically the minimal component in the LLM, right? They are just we can use some algorithms to transform the raw text into some token and assign each token with a number that we can use for training. Then we're gonna use these data to train a model with specific architecture. So if we have different goals when we train a model, we can choose different architecture. For example, the GPT model is used to predict the next token. And if we want to do some tests, we can use the BERT model. And there is also a new kind of model called Mamba, which is very popular today. So when we talk about training a chatbot like ChatGPT, our goal is to just predict the next token, which is called the next token prediction. And then we want to scale the model as much as possible because as a very classical paper suggests, when we scale the model depth, the data we use, and the computational time, we have a promisingly results that the model gonna perform better in various aspects. However, if we only do the pre-training part in training a model, they're gonna be very uh, terrible performance. For example, I have a screenshot from Andrew Kapasi's videos about how to train a GPT-2 model from scratch. And after doing the training part, and I got this sample from here. So it was prompted by, "Hello, I'm a language model," and it goes like this. For example, the first one, "Hello, I'm a language model, and I've been thinking a lot already since we did in the first episode, but what are we trying to do?" So we can see that after the pre-training, the model can generate some very coherent sentences, but but it is not it does not have any meaning, right? So I concluded into three reasons about this behavior. First, the training objective, which is the next word prediction, isn't we expect to utilize. For example, for chatbot, we're gonna use it for educational purposes. For example, teach others about maybe science, math, literature, or something, and maybe we want them to generate code. However, this is not what we do to train a model. We only want them to predict the next word coherently. Second, the data we used are for different purposes and vary in quality. So the original data we fetched from the web is from different sources, and they may have different purposes. And that's why it is maybe not so fit to train a model. Third, the expectations of the model are not the same as data distribution. In other words, the model learns a lot of knowledge and we only want them to comprehend a part of them. So I'm going to use an example from the original paper of direct preference optimization, which we're going to introduce later. This paper, and it goes like this. So if we have a coding problem and the chances of a human to pass this code uh, uh, code exam is like 50%. However, if we ask our chatbot to generate code to solve this problem, we only want them to give us the correct answer. That's why we say the expectations of the model are not the same as data distribution, right? So next step of training an LLM is supervised fine-tuning, right? So it consists of two steps. The first is to collect instruct following dataset. For example, researchers from Stanford University constructed a dataset called APACA dataset, in which we have some instruction following samples, and they want to train the model to follow their instructions. Then we're going to do the training on the foundation model, which is trained on a large amount of raw data. So the goal of this phase is to make LLMs understand the language better and enable them to generate coherent and contextually appropriate responses. The second goal is tailor the model to specific use. For example, translation, generation, or emphasize the model's capabilities in other aspects. For example, reasoning, doing math, or generating some poems. However, there are some drawbacks of supervised fine-tuning, right? So although it is the most direct way to make the model perform actions as we expected and improve their capabilities in some aspects, however, in some special situations, it is not so efficient. First, when we lack high quality data, or we need expert knowledge to get these data, which is prohibitively expensive, we are not going to use this because we don't have the prompt and the answer pair to train the model. Second, the supervised fine-tuning can't perform well when only the preference can be given. For example, in poetry generation, right? So I don't think there is a certain kind of best poetry given a theme. So that's why only preference can be given, right? So the next step is to avoid these drawbacks, we can use RLHF. So in this process, we're going to avoid suboptimal and undesirable responses and instill human values into LLMs. So, so some of you may wonder why we still need the supervised fine-tuning stage. That's because we want to enable the training to focus on subtle part as we instill much of the world knowledge into the model through the training and the fine-tuning stage. And second, we want to reduce the training cost and time, right? So I'm going to tell you about the pipeline of RLHF, and I think it's given in the previous talk in AI interest group. So the goal of RLHF is to make the model perform actions as we expected. So it consists of 4 steps. So first, we collect human labeled data on some downstream tasks. And we use data to do supervised fine-tuning on a model and sample 2 outputs with the prompt. Third, we use human annotators to judge which one is better, right? So here we get the preference of the data from the human. And fourth, we use target model to interact with the reward model and use the error-based algorithm to train the target model. So here, the reward model is basically trained by the preference data, and it can reflect human value, right? So this is the picture from the original paper of direct preference optimization, and it is illustrating the RLHF process, right? So, however, there are some drawbacks of RLHF. So first, we must train multiple LLMs in the RLHF process, which brings about tremendous computational cost, and it's hard for beginners to comprehend use, right? So we have a model to interact with the environment, which is the reward model. We have a maybe called a fixed model, right? And so I think, well, we may just need like 3 to 4 models at a time, which have a very heavy computational cost. The second is during the RL process, LLMs have to interact with each other and may lead to unstable performance. Third, there are a lot of hard parameters to tune in the training process, right? So for example, we have things like the gradient step or beta or many other things here. So we just can't figure out which hyperparameter we're gonna use to have an optimal solution to train a model, right? So this is very annoying sometimes, and maybe cost a lot of time and money to get the optimal solution. The fourth, the model tend to hack the reward instead of improving itself. So I'm going to tell you about reward hacking later. So the definition of it is an AI system try to get a reward by achieving the literal formal specification of an objective without actually achieving an outcome that programmers intended, right? So It is very obvious just from the name reward hacking, right? So it hacks the reward. So for example, uh, according to one experiment, uh, as GPT-4 model favors the long sequence input, when they're used to grade two responses, the model can learn to generate longer responses instead of uh, generate responses with higher quality to get a better grade from the GPT-4 model. And this is another example from the book, The Alignment Problem. And I think it's a pretty good book. So uh, you can just look at it for 30 seconds. Right. So now we have some knowledge about what is reward hacking, and then I'm going to introduce you to our new training algorithm, which is the direct preference optimization algorithm. So it has some key characters. So first, its use of change of variables to define preference loss as a function of the policy directly. And I will explain it later, use some mathematical expressions. Second, the arrow-based objective can be replaced by a simple binary cross entropy loss objective, which means the DPO algorithm is somehow very similar to the training of a supervised fine-tuning. Third, a dynamical per example importance weight that prevents the model degeneration. So here degeneration means the decrease in the performance of a model. So the pipeline of direct preference optimization is very simple. And first, we sample some output from the model and label them with human preferences. And then we use the algorithm itself to optimize the model to minimize the loss function. We can compare it with the former RLHF training process, and we can see that it is very simple to use from this diagram. So now I'm going to introduce you to the BT reward model, which is the Bradley-Terry model. So as we know, not only the DPO model, but also the DPO algorithm, but also the RHF algorithm, we have to get a reward model to train our role model. So first, we need to convert our human preferences into such model, and we have some kind of model to model the model's preferences. So it goes like this. So basically, we need to convert inputs into numbers, and this is where we need the reward model. So it's kind of simple, right? This is kind of softmax activation function, and the result is between 0 to 1, which is looks like a rate, right? And then we do some transformation of this reward model to look a bit simpler, right? And the ROHF loss function looks like this. It basically go over all over the data set and and use the model to get the loss, right? And so what's more, we have to add a KL divergence in our loss function. So this added term is basically a measure of how one probability distribution P is different from the second one. So we do not want the model to go very far from the original model. So we use this term to control it, right? Then we adapted this KL divergence to our training context, where only one X in the dataset is sampled, and we can get the final ROHF objective, right? So here from this equation, we want to maximize our preference as the human preference without get too far away from the original model, right? So there are three notes here. So the objective is to maximize the rewards using PPO, which is a error-based algorithm to solve this this optimization problem. And this term here can be any kind of reward model. And in our example is the Bradley-Terry model, which we introduced earlier. And the third one is the bigger, better is the less change will be added to the model, right? So it's very easy to see. However, consider the drawbacks of RLHF. We want to design a simpler algorithm to train our model and align our model to human goals. So the motivation of it is very simple, which is called the exchange of variable. So this is an example generated by ChatGPT, and we can see from it is, so maybe many of you have learned it in primary school, and I think it's very simple. So here, we're going to derive the direct preference optimization objective, which is the loss function. However, I know many audience in this channel may be not so familiar with some complicated math operations. So I'm going to give you some insights of it. And if you are interested in what's going on behind the hood, I have a detailed explanation of each step of deriving the objective in my PowerPoint. And you can just see it after this talk, right? So one of the disadvantages of RLHF is that there are many models interacting with each other. So we want to remove the reward model from the loss function. And so first, we just do some transformation here, right? And yeah, finally, we through some transformation, we get a final equation without the reward function, right? So the question now comes to how to minimize the following equation. Then we want to get the optimal solution from the previous equations here, and according to this theory, we know that this is minimized when they're equal to 0, which means two distributions are the same. So we can get the final optimal solutions here, and we can see it is pretty simple compared to the previous loss function. And we can derive the reward model from here. However, if we want to compute the value of zx, we have to compute all the x from dataset, which is prohibitively expensive, and its computational complexity increased linearly. So we want to cancel this term here, and then we can get the final objectives here. And we can see here that the loss function in terms of the policy is not the reward function, and we can optimize it through the gradient descent, which is kind of the same as the supervised fine-tuning, right? So let's review the key characters of direct preference optimizations here. So first, we use change of variable, right, to remove the reward function in our loss function. And then we have an RL-based objective, which can be replaced by a simple binary cross entropy loss objective. Third, a dynamic per example importance weight that prevents the model degeneration. Right. and we're going to introduce the third part later. So one thing to add that I know maybe some of you don't know what's cross entropy loss, and it's just look like this. So let's have a look about how gradient update do, and we're gonna know exactly what the model do when training. So basically, the first part here, make sure that uh, uh, the model get a higher weight when the reward estimation is wrong, which is a dynamic, for example, importance weight, right? And the first part here increase the likelihood uh, of getting the same answer of a reward model, and here is a decreased likelihood of the negative example, right? And we can see there's a hyperparameter here called beta, and it controls how large the gradient steps is. Then we have the SIMPIO, which is a variant of drug preference optimization. And the motivation of this research is that the researcher observed the discrepancy between how the model is trained and how the model is inferenced, leading to suboptimal performance. And it just changed the equation here and gets a better result here. So if you guys are interested in this variant, and you can just look at the paper, right? So it has two main characters. So first, it has a length normalization calculated as an average log probability of all tokens in the response. Then we can have a target reward margin to ensure the reward difference between winning and losing responses exceeds this margin, right? So I think it's pretty easy to comprehend. And then we're going to talk about the application of this algorithm. So basically, it has two main kind of application. First, we can use it in the alignment part in the LLM training procedure to align the model behavior to human goals. Second, we can use it to fine-tune a model for specific use, for example, in poetry generation. So the first use case of it is use the DPO algorithm in the LLM training. So due to the computational efficiency of DPO algorithm and stable performance, some teams use this instead of RHF in the training process. For example, maybe in this summer, the LLaMA 3.1 models from Meta use direct preference optimization algorithm to align the model with the human goals to get a better performance, right? And I think it's here, right? The LLaMA 3.1 here. And the second use case is basically the same as supervised fine-tuning. However, there are some advantages. For example, in some scenarios when only preference can given, we can use this algorithm to get a better result. For example, the control sentiment generation or summarization, single turn dialogue, or some customized output. And we can get a result from the original paper that the DPO trained model performed as well as the RHF model, and sometimes even surpass it in some tasks. Right. So let's come to our final part, which is a hand-on tutorial on how to train a medical chatbot using direct preference optimization algorithm. So first, we get some medical QA data from Hugging Face, right? And we sample 3,000 data from it. Then we get negative sample using GPT 3.5 Turbo. So I assume here that the GPT 3.5 Turbo performs worse than human, right? And we're going to use an all-in-one method, which I'm going to introduce later. So we're going to use LLaMA-Factory from Hugging Face to train our model, right? So basically, Hugging Face is an all-in-one uh, training platform, which we can use to perform various training algorithms like supervised fine-tuning, preference optimization, and many other things in one platform. And so its advantages is first, it is computationally efficient and time saving. Second, it has detailed explanation about how to train a model and shows me the diagram of training loss and validation loss. However, have some disadvantages, which is it is not so flexible and we don't know what's going on under the hood. Right. So so here I have already trained a model using the using such data, and we can see this is our training data here. So we have an instruction. For example, this is such kind of disease which I'm not familiar with, and this is the chosen response which is given in the original data set. We can see it's pretty professional and it's of good quality. And the rejected responses are generated by GPT 3.5 Turbo, and I think it's kind of general and not so meaning. I don't know. So maybe some of you can know about the relative quality of this better than me, right? So I use such kind of comparison data set to train my model, which I think it's I think it's the Chen 2 model instructed, and this is the page in GitHub of LLaMA-Factory, and we can see from it has detailed explanations and support for various various models. Right. So let me show you how to use this model. Use this lib. So first, first you have to clone this this repo to your own device, and make sure you have something like a GPU or something, right? So here, I have the so here I only have a 419 GPU here, and I will be able to train a 7 billion parameters model, which cannot be achieved using any other approaches. So after we clone this lib from GitHub, we have to put our data set here, and right, it's here now, and add some descriptions in the dataset information part here. So here I add my medical QA dataset and the file name, and assign my name to this, and then we're gonna use direct preference optimization algorithms here. Here I'm gonna change this. I use Chen 2 7B instruct and do DPO training, and this is my data set and template, which is a predefined template for different model. And cutoff length basically means how many tokens you can use training. Max samples means how many data you're gonna use in the training process. We can see that it has a lot of parameters to uh, it has many annotations, and you're gonna know what parameters you're gonna do even if you are new to these algorithms, and you can change the batch size, the training epochs, and validation size here. And I can show you some how to train this. So first, uh, I need to create a virtual environment. Uh, so let's activate it. And it has yes here. Yeah, and we copy this. Install some dependency, uh, some lib. So basically, this repo is based on uh, many other tools to make sure that you can train the model with a very low computational cost. So see, it's a lot. So basically, I have already trained a model here, and I can show you how it responds to some medical problems. Okay. I think we should just wait some more moment to see. So, uh, yes, and uh, wait here. We can see how the model, uh, how training process goes on. Right, so it's downloading the model from the web. Now it's converting the format of dataset and run the tokenizer. Right, that shows an example of the label, and uh, continue downloading the model here and loading the model weights. So here I'm going to prepare a medical uh, uh, medical uh, for example, parasites. Parasites. this. Uh, still, oh, yeah. So here is the training arcs, and it start training here. You can see it has 160 68 steps here, and it has an estimated time which is 41 minutes. Right. So it's very fantastic. We are going to show the training here. So let's just inference train the model here. Wait. Yes. So it's loading the model. Yes, in the user here. And we have an adapter which I trained previously. Ask how to cure parasites. We can see it's the speed of generation is pretty fast, and it gives some pretty useful advice, I think. All right, consider we only have a 490 GPU. Yeah. So let's go back to PowerPoint. So, however, in a newly published paper, questioned the effectiveness of drug preference optimization algorithm compared to RHF, which is called is DPO superior to PPO for AI alignment, a comprehensive study. We can show that the PPO performs better in some scenarios. However, we can do something to improve the performance of drug preference optimization algorithm here. So it gives us two suggestions when performing drug preference optimization. First, we can use additional supervised fine-tuning to make the model adapt to distribution in training data. Second, we can use online sampling during the training. So this is what we gonna try in the future, right? And if you guys are interested into this study, I put the links here. And I think this is all for today. So we review of the RLM training process and introduce the drug preference optimization algorithms. And I hope all of you guys can learn something from today's tutorial. And thanks for listening.